Welcome to Deep Thinkers. Tonight, before you let the day fall away from you, I want to give you something to hold in the quiet. Not a worry, not a task. Just a single, slow, astonishing thought to turn over gently in the dark until sleep finds you. So settle in. Let your shoulders drop away from your ears. Let the weight of your own body press down into the mattress, the way a stone settles into a riverbed, unhurried, exactly where it belongs. And let me tell you about a day that lasted only 6 hours. There was a time, long ago, so long ago, that the number almost refuses to mean anything, when the sun rose and set in the span of a single afternoon. A morning, a noon, a dusk, and then darkness again, all of it folded into about 6 hours. If you had stood on the surface of the young earth, and if there had been any ground solid enough to stand on, and any eyes to see with, you would have watched the whole sky wheel overhead at a pace that would make you dizzy. The sun climbing, cresting, falling, and the stars sweeping past in a rush. One full turn of the world every 6 hours or so. The Earth was spinning that fast. It was a young planet, and like most young things, it was in a terrible hurry. That is where our story begins. About 4.5 billion years ago. And to understand a 6-hour day, you first have to understand where the moon came from. Because the two of them, the Earth and the moon, have been telling a single story ever since, a story that is still being told tonight, right now, above the roof over your head. The leading idea, the one most scientists hold to, is called the giant impact hypothesis. And the picture it paints is this. In the earliest days of the solar system, when the planets were still gathering themselves out of dust and rubble and molten rock, the young Earth was not alone in its orbit. There was another body sharing that same lane around the Sun. A world about the size of Mars. Scientists have given it a name. They call it Theia. And Theia and the proto-Earth were on paths that could not both continue forever. Slowly, over ages, their orbits drew them toward the same point in space at the same moment. And then they met. Now, when I say they met, I do not want you to imagine a sharp collision, a crack, a bang. The mind reaches for those sounds, but there was no one to hear them, and space carries no sound anyway. Instead, imagine something slower and stranger and almost silent. Two molten worlds, glowing, folding into one another over hours. A grazing, catastrophic merging. Theia buried itself into the young Earth, and in the violence of that union, an enormous cloud of vaporized rock and debris was flung outward. A great glowing ring of shattered material spun off into orbit around the wounded, reforming planet. And out there, in that ring, gathering itself the same way the planets had gathered, cooling and clumping and pulling itself together by its own faint gravity, the debris became the moon. So the moon is, in a sense, made from us. From the outer layers of the Earth and the body of Theia, mingled and thrown skyward and reassembled into a companion. And when that companion first took shape, it was not the small, distant silver coin you see on a clear night. It was close, astonishingly close. Where the moon today sits at an average distance of about 384,000 kilometers from us, the newborn moon may have hung at only tens of thousands of kilometers away, a tenth of its present distance, or less. Close enough to fill a vast portion of the sky, close enough to loom. Picture that for a moment, gently, the way you would picture a scene in a dream you are already half inside. A moon many times larger than the one we know, hanging heavy and enormous over a molten, restless Earth. And that moon, being so near, pulled on the young planet with a grip hundreds of times stronger than it does now. The tides it raised were not the soft rise and fall of water on a beach. They were mountainous. They moved through rock and through whatever seas were forming, immense and relentless. And the earth beneath it spun, and spun once every 6 hours or so, dizzy and young and fast. That is our starting frame. Hold it lightly. A fast little world, a giant near moon, a day only 6 hours long. And here is the thought I want to lay beside you for the whole of tonight, the single quiet idea this entire story circles around. The day is not a fixed thing. It never was. We treat 24 hours as though it were carved into the nature of the universe, as though it had always been and would always be. But it is not a constant. It is a single frozen frame plucked out of an immense and continuing motion. The day you lived today, the 24 hours you are now letting go of, is longer than the day the dinosaurs knew, and far longer than the day of that young spinning earth, and it will be longer still for whatever comes after us. The day is not a wall. It is a slow exhalation, a breath the planet has been letting out for 4.5 billion years and has not yet finished. So the question that pulls us forward through the dark, the question I want you to carry down towards sleep, is simply this. What stretched it? What took a 6-hour day and drew it out, patiently, over billions of years, toward the 24 hours we live in now? What is doing the pulling, and could it ever stop? We are going to answer all of that tonight, slowly, with no rush at all, the way the process itself has no rush. And I promise you, you do not have to stay awake to the end. There is no test. There is no ending you will miss. This is a story built to be drifted through, and if sleep takes you somewhere in the middle of it, then you will have fallen asleep inside one of the largest and gentlest motions in the whole of nature, and there are far worse places to fall asleep than that. Before we go deeper, let me ask you one small thing, and then I will not interrupt the quiet again. I would love to know where in the world you are listening from tonight. Whatever city, whatever room, whatever hour it is where you are. If you feel like leaving that in the comments, I read them. And there is something I find genuinely comforting about it. All these different lights going out in all these different places, all of us under the same slow-turning sky. And if these long, slow journeys help you find your way down into sleep, you might quietly subscribe so that the next one finds you when you need it. That is all. Now let the day keep going. So, what stretched the day? What is doing the pulling? The answer has a name, and it is a plain one. Tidal friction. And to understand it, we have to talk about the tides, but slowly and gently, because the whole thing is gentler than it sounds. You already know the tides in your bones, even if you have never lived near the sea. You know that the ocean rises and falls, that twice a day the water creeps up the sand and then slides back down again. And you may know that the moon is the cause of it. But how it causes it is the quiet, beautiful part, and it is worth going into softly. The moon has gravity, as all things with mass do. And gravity does not pull on everything equally. It pulls harder on the things that are closer. This is the whole secret right here, and it is such a small thing. The side of the Earth that faces the moon is a little closer to the moon than the center of the Earth is, and the far side, the side turned away, is a little farther still. So the moon pulls hardest on the near side, and less hard on the center, and least of all on the far side. And that difference, that gentle unevenness in the pull across the width of the whole planet, is enough to stretch the Earth ever so slightly, into a shape that is not quite a sphere. It draws the oceans, and even the solid rock itself, out into two soft bulges. One on the side, facing the moon, pulled toward it, and one on the side facing away, left behind as the rest of the earth is tugged forward. Two bulges, one under the moon, one directly opposite it, on the far side of the world. This is why there are 2 high tides a day, and not one. The water is heaped up on both sides at once, near and far, and as the earth turns beneath those 2 heaps, any given shoreline passes under first one bulge, then the low water between, then the other bulge, then low water again. The bulges themselves barely move. It is the earth that rotates through them, carrying the coastlines past the standing swells of water like a slow wheel turning through 2 fixed hills of sea. Now, if the story stopped there, if those 2 bulges simply sat perfectly beneath the moon and perfectly opposite it, then nothing would change. The earth would turn through them forever, and the day would never lengthen, and I would have no story to tell you. But the story does not stop there, and the reason is the single most important detail in everything I am going to say tonight. So let me lay it down slowly. The earth spins fast, faster than the moon moves. The earth turns all the way around once in about 24 hours. But the moon, up in its orbit, takes far longer to go around the earth. It takes about 27 days to complete one full circuit, one full loop around us. 24 hours against 27 days. The earth is spinning far, far faster underneath than the moon is drifting around above. So here is what happens, and I want you to see it as clearly and calmly as you would watch a leaf carried by a slow current. The tidal bulge wants to sit directly under the moon. That is where the moon's pull is trying to hold it. But the earth is rotating so quickly that it drags that bulge along with it, forward, ahead of where the moon actually is. The spinning body of the planet, with all its friction, all its dragging of water over the ocean floor and rock through rock, carries the near side bulge a little bit ahead of the Earth, moon line, before the water can settle back down. The Earth's rotation is faster than the bulge can respond, and so it hauls that heap of ocean forward, out in front of the moon, like a runner pulling a scarf ahead of the wind. So the bulge is no longer directly beneath the moon, it runs a little ahead of it. And this is where the whole future of the day is decided, in this one small offset, this slight leading of the tide. Because that bulge, that great soft heap of ocean and rock hauled slightly forward of the moon, has mass, and anything with mass has gravity of its own. So the bulge pulls on the moon. And because the bulge is running ahead, out in front of the moon, along the direction of the Earth's spin, its gravity does not pull the moon straight down toward the Earth. It pulls the moon a little bit forward along the moon's own path. It is a small tug, always in the same direction, never resting, a faint, steady hand on the moon's back, urging it onward in its orbit. And when you tug a moon forward along its orbit, when you add a little energy to it that way, you do not make it go faster in the sense you might expect. You lift it. You nudge it into a wider, higher, more distant orbit. The forward pull of that leading bulge is, slowly and endlessly, pushing the moon farther away. Quick reminder before we go on, and then I will let the story carry us again. After years of lying awake with a racing mind, deep sleep finally became possible for me. And once it did, everything changed. Learning came easier, the energy was real, the mind stayed sharp through the whole day. Sleeping like a baby, night after night, changed everything. If you want the exact system that made that possible, it is in the link in the pinned comments, waiting there quietly for whenever you want it. That is all. Now let the moon keep drifting. So the leading bulge pulls the moon forward, and the moon rises, year by year, into a wider orbit. That is one half of the exchange. And here is the other half, the half that concerns the day, the half you have been waiting for. The moon pulls back. Newton told us this long ago, that for every pull there is an equal pull the other way. If the bulge is tugging the moon forward, then the moon is tugging the bulge backward, just as hard. And the bulge is part of the Earth. It is the Earth's own oceans, the Earth's own body, hauled out of shape. So when the moon pulls back on that forward-running bulge, it is pulling backward against the very direction the Earth is spinning. It is a break, a soft, constant, gentle break, laid against the whole turning of the world. The moon is holding the leading tide back, trying to drag it into place beneath itself, and in doing so it is very slightly, very patiently, slowing the Earth's spin. Every day the moon presses back against that runaway bulge. Every day the Earth's rotation gives up the tiniest sliver of its speed. The planet is turning through its own tides, and the friction of that turning. Water dragging over the shallow sea floors, rock flexing against rock, is bleeding the spin away. That is tidal friction. That is the whole engine of it. The Earth spins, its rotation flings the tidal bulge ahead of the moon pulls that bulge backward, and the backward pull slows the Earth, while the forward push lifts the moon away. Two things happening at once, forever locked together. The Earth slowing, the moon retreating, one motion seen from two sides, and I find something deeply calming in the shape of that, something worth resting on for a moment before we go further. There is no violence in it, there is no sudden event, no catastrophe, no drama. There is only a slow and constant giving. The Earth is spending its own spin, a little each day, and the moon is receiving it, a little each day, and neither of them is in any hurry, and neither of them can stop. It is one of the oldest exchanges in the solar system, older than the oceans in their present shape, older than every living thing, and it has been going on with the same soft patience the entire time. The tide that pulled the sea up your local beach this afternoon is the very same tide, the very same bulge. That is at this moment slowing the Earth and letting the moon go. The rising water and the lengthening day are not two facts. They are one fact, felt in two places. Let me draw the mechanism once more, slowly, because if you carry only one image down into sleep tonight, let it be this one, and it is worth setting gently in place a second time. The Earth turns, fast, once every 24 hours. The moon hangs above it, moving slowly, once around every 27 days. The moon's uneven gravity lifts two bulges of ocean out of the sea, one beneath it and one on the far side. But the Earth is spinning too fast for those bulges to stay put, so it drags the near one forward, ahead of the moon. The forward bulge tugs the moon onward and lifts it into a wider orbit. And the moon, pulling back on that forward bulge, drags against the Earth's spin and slows it down. The moon climbs away. The day grows longer, grain by grain, breath by breath, across 4.5 billion years. That is why the 6-hour day of the young Earth did not stay 6 hours. From the very moment the moon formed out of that ring of shattered rock and settled into orbit, this exchange began. The near moon raised enormous tides, and those enormous tides were dragged ahead by the fast-spinning Earth, and they hauled the moon outward and braked the planet from the first turn onward. The Earth has been slowing for as long as it has had a moon. The day has been lengthening for as long as there has been a day worth naming. And notice, gently, what a strange and lovely thing that means about the moon you know. The moon has not always looked the way it looks tonight. It was once a great near thing, filling the sky, raising mountainous tides on a molten world. And it has been walking away from us the whole time since, slowly, faithfully, without ever once turning back. And it is smaller in our sky now than it has ever been, and it is still going. The distance between the Earth and the Moon is not a fixed measurement. It is a gap that has been widening for billions of years and is a little wider tonight than it was the night you were born. Now, you might reasonably ask, if the Moon began so close, tens of thousands of kilometers away, and it is now 384,000 kilometers away, and it has been climbing outward this whole time, then how fast is it actually moving? How quickly does a moon walk away from its planet? And the answer is one of my favorite numbers in all of science, because it is so small and so tender and so easy to hold in the palm of your mind. But that number and the mirrors on the moon that let us measure it and the lasers we bounce off them, we will come to in a little while, because they belong to the next part of the story, and there is no need to hurry toward them tonight. For now, stay here, in the deep past, with the young Earth turning fast beneath its giant near moon. Feel how far away that is, how long ago. 4.5 billion years. The number is so large, it stops being a number and becomes a kind of darkness, a depth you can sink into. And every one of those years, the Earth has been slowing, by an amount so small no single lifetime could ever feel it. And yet across all those years, it has added up to 18 hours. 18 hours of day, drawn out of the planet's spin and handed, quietly, to the moon's long climb. Let me hold you in the strangeness of the early Earth a little longer, because it is a good place to rest, and because the slowness of what happens next is easier to feel once you have felt how fast things began. That young world was not the blue and green place beneath your feet. It was molten in many places, its surface still cooling from the heat of its own formation and the heat of the impact that made the moon. There were no continents as you would know them, no oceans in their familiar basins, no life of any kind, not the faintest single cell. There was rock and heat and a fast, dizzy spin, and above it all that enormous moon, so close it would have seemed to press down on the sky. And the tides in that first age were not water lapping at sand. They were the whole flexing body of the planet, heaving up and down under the moon's near grip, hundreds of times more powerful than anything the sea does now. The young Earth and the young moon were locked in a fierce and intimate embrace, pulling at each other with a strength we will never see again, and it was in that fierce early time that the slowing began, strongest of all. Because the tides were strongest of all, and strong tides break hard. And then, as the moon drew back, as it climbed away year by year into a wider orbit, the tides it raised grew gentler, and the breaking grew gentler with them, and the whole exchange settled into the slow, soft, almost imperceptible motion we live inside now. The fierce embrace of the beginning became the long, quiet companionship of the present. The moon that once loomed became the moon that watches from far off, and the day that once flew around in 6 hours slowed and slowed and slowed into the 24 hours you are letting go of tonight. So that is the beginning of the exhalation. A 6-hour day, a giant near moon, a fast molten world, and the tide, born in that first age, that has been doing the same slow work every day since, dragging ahead, tugging the moon out, pressing back against the spin. Letting the day grow, it is happening right now, above your roof, beyond the dark. The bulge is out there, hauled a little ahead of the moon, and the moon is pulling back on it, and the earth is turning through it, and tonight is a hair longer than any night before it in all of history. We have the beginning, then, we have the newborn earth and its close moon, born together out of a collision 4.5 billion years ago. And we have the engine, the tidal friction, the two bulges, the leading tide dragged ahead by a fast spin, the moon lifting away and the day drawing out, one breath at a time. We have the great slow motion in which every night you have ever slept is a single frozen frame. But a mechanism is one thing, and proof is another. It is a beautiful story, the tide slowing the world. It has the shape of truth. And yet how could anyone ever know it is really so? How could anyone measure a change so small that 1,000 human lifetimes stacked end to end would barely feel it? How could anyone stand on the earth and say, with any confidence at all, that the day is longer now than it was when the great reptiles walked? Or longer than it was in some warm, shallow sea 400 million years ago, and prove it, not with a story, but with something you can hold in your hand? That is where this journey goes next. Because it turns out the Earth has been keeping records the whole time. Quiet records, written not in books but in stone, and in coral, and in ancient mud, and in the shadows of eclipses, watched by people who have been dust for thousands of years. The lengthening of the day has left its fingerprints everywhere, if you know how to read them. And there are creatures long extinct that counted the days for us, without ever knowing they were counting, laying down one thin band for every turn of the world, so that we could hold their skeletons up to the light and count the sunrises of a vanished year. But that reading, and the mirrors on the moon, and the lasers, and the corals that saw 400 dawns in a single year. All of that is still ahead of us, waiting quietly in the dark like the rest of the night. There is no need to reach for it now, for now it is enough to lie here, with the young earth spinning fast beneath its giant moon, and to feel the first slow pull of the tide, beginning the long, patient work of stretching the day, and to know that the same pull is at work tonight, above you, unhurried, letting the moon go by the width of a fingernail's growth, drawing this night out by a sliver too fine to feel. The world is slowing. It has always been slowing. And there is nothing to do about it, and nothing that needs doing, only to rest inside it the way you are resting now. Let the earth keep turning. Let the tide keep pulling. And let us go on, slowly, into how we know. There is a principle at the heart of all of this that is worth sitting with for a moment, because it is one of those ideas that appears at first to be a dry piece of physics, and then slowly reveals itself to be something stranger and more beautiful than it first seemed. It is the principle of conservation of angular momentum, and what it means, in the plain language of this particular story, is that nothing is being lost. Nothing has ever been lost. The spin that the young earth carried inside it, in those first dizzying hours when a day lasted only 6 hours and the moon hung enormous and close, and the tides ran hundreds of times taller than anything alive today has ever witnessed. That spin did not simply disappear as the planet slowed. It went somewhere. It went into the moon. Think of it this way. When a figure skater draws her arms inward, she spins faster. When she extends them again, she slows. The motion redistributes, but the total quantity of spin contained in the system, the angular momentum, stays constant. No one is adding anything, and nothing is escaping. The system simply rearranges itself, trading rotation for a different kind of motion. And the accounting always balances. The Earth and the Moon are that system. They have been that system for 4.5 billion years. And what has happened over all of that immense and patient time is a slow rearrangement. The Earth has been giving its spin to the Moon, and the Moon has been carrying it away, and the result is that the Earth turns more slowly today than it did yesterday. And the Moon is a little farther from us today than it was yesterday, and both of these facts are the same fact, expressed in two different places. This is what physicists mean when they say that angular momentum is conserved in the Earth-Moon system. It is not a statement about loss, it is a statement about transformation. The spinning of the Earth does not vanish into nothing. It flows through the mechanism of the tides, outward, into the Moon's orbit, lifting the Moon higher and higher on a slow spiral that has been ascending without interruption since the Moon first formed. The Moon is climbing. It has always been climbing, and every foot of that climb is paid for by a fraction of the Earth's rotation, a sliver of the day. The merest thread of speed drawn out of the planet's turning and deposited, like a quiet tithe, into the distance between us. The ocean floor is where the accounting gets physical. When the tidal bulge heaves through the sea, dragged around the planet by the Earth's rotation faster than the Moon can keep up, the water is not merely shifting in place, it is grinding. It is sloshing against the edges of continents, surging over the shallow, rough terrain of the seabed, pressing against coastlines and undersea ridges and the broad continental shelves where the water is not very deep and the friction is very great. And that friction generates heat. The motion of the ocean, driven by the pull of the Moon and resisted by the floor beneath it, produces warmth. It is warmth you will never feel. Spread too thin and too deep and too widely across the planet's surface to register in any thermometer you could carry. But the numbers are real. The energy flowing out of the Earth's rotation and into the gentle warming of shallow seas is on the order of a few terawatts. A terawatt is 1,000,000,000,000 watts. Human civilization, at any given moment, uses roughly 20 terawatts to run every machine and light and engine on the planet's surface. And the tides, silently, are dissipating energy on that same approximate scale, drawn not from any fuel or chemical process, but from the rotation of the world itself. The Earth is its own power source, slowly unwinding, and the cost of the Moon's slow retreat is paid in the warmth of the ocean floor. It is an old expenditure. It has been running for as long as there has been a Moon, and before that, in a different form, for as long as there has been an Earth. But the rate has not been constant. It has varied with the arrangement of the oceans and continents, swelling when geography placed tidal water near resonance, and quieting when the seabed was arranged in ways that let the water move more freely. The present rate, the one we can measure, is in fact anomalously high, and understanding why that is and why it matters is a piece of the puzzle that will come a little later in this night. For now, the important thing is simply this: the energy is real, the transfer is real, and the Moon carries it away. And we can measure how far away it carries it. Since 1969, human beings have known the distance to the Moon not as an estimate or a calculation, but as a direct measurement made with light. The Apollo astronauts left behind, on the lunar surface, small arrays of glass prisms cut and polished to a particular geometry, retroreflectors. Each prism designed to return any beam of light that strikes it directly back toward its source, regardless of the angle of incidence. The Soviets left similar devices, carried to the Moon by their unmanned Lunokhod rovers. And from observatories on Earth, scientists have been firing laser pulses at those reflectors ever since, measuring the time it takes for the light to travel to the moon, bounce off the prisms, and return with a precision good enough to calculate the Earth-Moon distance to within a few millimeters. This is the technique called lunar laser ranging, and it has been running continuously now for more than half a century. What it has revealed, accumulated measurement by measurement over all those decades, is that the moon is not staying where it is. It is moving. Not in the sense of orbiting, which everyone has always known, but in the sense of retreating, drifting outward along its orbit, the orbital radius growing by a small and constant amount each year. The rate derived from the accumulating record of laser returns is approximately 3.8 centimeters per year. That is how much farther away the moon is, on average, at the end of any given year than it was at the beginning of that year. And 3.8 centimeters is roughly the speed at which human fingernails grow, which makes it one of the more useful coincidences in all of science communication, because it gives you something to look at, something on your own body, when you want to feel the scale of what is happening. Your nails grow, and the moon retreats at approximately the same pace. The same slow accumulation. The mean distance from the Earth to the moon today, averaged over the elliptical wobbling of the orbit, is about 384,400 kilometers. That number has been climbing day by day at 3.8 centimeters per year for as long as the mechanism has been running. And the same mechanism that carries the moon outward is the one that stretches the day. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments, because the two are the same process, seen from different vantage points. Every centimeter of lunar retreat corresponds to a transfer of angular momentum from the Earth's rotation to the moon's orbit, and every transfer of angular momentum slows the spin of the planet by a tiny fraction. The day grows longer. By how much? On the long astronomical average, by roughly 1.7 to 2.3 milliseconds per century. The commonly cited figure is close to 1.8 milliseconds per century. A millisecond is 1,000th of a second, and a century is 100 years. So in the entire span of a human lifetime, roughly 80 years, the day lengthens by something in the neighborhood of 1.5 milliseconds. Less than the blink of an eye. Far less than any human nervous system could perceive. A change so small that it requires atomic clocks, the most precise timekeepers ever made, to detect it at all. And yet it compounds. It has been compounding for 4.5 billion years. And when you stack milliseconds across millions of centuries, the numbers become something you can see in the world. 100 million years ago, when the last of the non-avian dinosaurs were alive and moving across warm floodplains and shallow inland seas. The day was not 24 hours long, it was closer to 23.5 hours, and because the year, the time it takes the Earth to complete one orbit around the Sun, does not change appreciably with any of this, a shorter day packed more of them into each year. Where we have 365 days in a year, those ancient creatures had roughly 372. 372 sunrises, 372 cycles of light and dark, each one a little shorter than the ones we move through now. The tyrannosaurs, whatever time sense they possessed, moved through a world that turned slightly faster than ours. Their shadows shifted at a marginally different pace. The sky moved just a fraction quicker overhead. It would not have been noticeable, not in any single moment, not in any single life. But it was real. And it is knowable. The knowing is what makes this particular science so quietly astonishing. These are not speculative numbers, not extrapolations from a theory in a vacuum. They are grounded in measurements, in physical evidence, in the patient accumulation of data from instruments and from fossils and from records left by civilizations long dissolved. The slowing of the Earth is not inferred from equations alone. It has been measured in several different ways, by several different methods, and they largely agree. The day is getting longer. The moon is receding. The angular momentum of the Earth is slowly becoming the orbital energy of the moon. And the world's timekeepers have had to respond. Since 1972, the international system of civil time, the coordinated universal time that governs every clock and every network and every scheduled thing on the planet's surface, has periodically added an extra second to the calendar. These are called leap seconds. They exist because atomic clocks, the ultra-precise instruments that define the modern second, keep time with almost no error at all, ticking to a standard derived from the vibration of cesium atoms, which is perfectly regular and entirely indifferent to the behavior of the planet beneath them. But the Earth does not keep atomic time. The Earth keeps its own time, defined by how long it actually takes to spin once relative to the Sun, a measure called UT1, universal time. And UT1 and the atomic standard called UTC, coordinated universal time, are not the same thing, because the Earth does not spin at exactly the rate that was used to define the modern second when the International Time System was set up in the mid-20th century. The planet turns a little slower than that, and so, every so often, when the gap between atomic time and solar time threatens to exceed a certain threshold, a leap second is inserted, a single extra tick added to the clock to let the Sun catch up. It is a strange kind of maintenance. The clocks of the world, the networks, the satellites, the computers synchronizing themselves to one another across continents and oceans are corrected for the behavior of a planet that is imperceptibly but measurably slowing its spin. The engineers who manage UTC watch UT1 drift and calculate, and they issue notices months in advance when a leap second will be needed, so that every system that depends on precise time can prepare. The year has, in some technical sense, a variable length at the level of individual seconds. The day is growing, and the calendar has to accommodate it. And yet, as a small and interesting wrinkle in this long story of gradual slowing, the trend in recent years has complicated the picture slightly. For a period between 2020 and 2024, the Earth was actually spinning a little faster than the long-term average, not slower. Several of the shortest days ever measured by modern instruments fell within that window. This is not a reversal of the long-term tidal braking, which continues unchanged over geological time. It is a short-term wobble driven by motions in the molten core beneath the mantle, by the redistribution of ice mass as glaciers melt and ocean water shifts, by other subtle rearrangements of matter within and on the planet. The Earth is not a simple, rigid ball spinning cleanly in space. It is a layered, fluid, dynamic system, and its rotation speed flickers slightly from year to year around the long downward trend. And in those years of slightly elevated spin, the gap between UT1 and UTC was being reduced rather than widened, which led for the first time to discussions among timekeepers about whether a negative leap second might eventually be needed, a second removed from the calendar rather than added. to prevent atomic time from falling behind solar time rather than ahead of it. The idea has no historical precedent in the history of the system. It would be a new kind of correction, and whether or not it ever proves necessary depends on how those short-term wobbles evolve against the long background of tidal slowing. The long background always wins, in the end. Geologically, it always has. The wobbles come and go, driven by ice and by the slow churning of the interior, by seasons and by the redistribution of water. But beneath all of them, patient and undeflectable, the tidal breaking continues. The moon pulls at the Earth's oceans, the bulge drags ahead of the moon's position, the torque transfers momentum outward, and the day grows longer. By its fraction of a millisecond per century, year by year and century by century, and million year by million year, compounding into the past and future alike. There is something almost meditative about it, when you lie still and let the scale of it settle. You are on a planet that has been slowing without pause for 4.5 billion years. The day you are inside right now, the one that started this morning and will end when the sun rises again, is fractionally longer than the day your grandparents were born into. Not noticeably longer, not measurably longer by any human sense, but longer. And the day they were born into was fractionally longer than the one their grandparents knew. Each generation inhabits a slightly longer day, carrying the accumulated slowing of all the centuries that came before it, and leaving behind a world rotating slightly more slowly for the ones that follow. It is the most gradual inheritance imaginable, a bequest so small that it takes instruments of extraordinary precision to detect, and yet it is real. And it has been real for as long as there have been days. The moon receives it all. Each fraction of a day's length that has been added over the history of the world corresponds to a parcel of angular momentum transferred outward, translated into distance, a few centimeters at a time, over billions of years, so that the moon today sits 384,400 kilometers away and continues to drift, year by year, outward still. The same process that once, in the beginning, had the moon hanging enormous and close enough to raise tidal walls hundreds of meters tall, has carried it to its present measured distance and will carry it farther still, on the same patient schedule, into whatever remains of the future. And the future, when you look at where all of this is heading, opens into a kind of dreamlike distance that is not frightening, or at least it does not need to be if you let yourself settle into it instead of grasping. But that horizon and the strange things the evidence shows about what happened in between, the billion silent years when the day stopped growing, and the ancient corals that counted sunrises for us, and the eclipses that Babylonian priests recorded on clay tablets so that astronomers 2.5 millennia later could measure how much the planet has slowed, all of that is waiting just a little further along in the night. There is no hurry. There is never any hurry in a story this old. For now it is enough to stay with the present numbers, to let them rest in the mind without clutching them. The moon retreating at the pace of a growing fingernail, the day lengthening by less than 2 milliseconds every 100 years, the ocean floor warming gently with the energy drawn from the planet's spin, a few terawatts of deep, untouchable heat. The tidal tax paid year after year after year, the clocks of the world carrying a small correction for the fact that the Earth does not quite keep the time the atoms keep. And beneath all of it, the conservation law, patient and absolute, nothing is being lost, only moved, the spin of the world slowly becoming the sky's greater circle, the day becoming the orbit, the moment becoming the distance. in a transformation so slow that no individual life can witness it, and yet so real that it has written itself into the bones of the planet and the stone of the seafloor, and the careful records of every civilization careful enough to watch the sky. The earth is turning beneath you now, more slowly than it turned last year. More slowly by a margin too fine to feel, too fine to see, too fine to measure with any instrument you could hold in your hands. But the instruments exist, and the measurements are real, and the lasers have been bouncing off the lunar prisms since 1969, accumulating their data, confirming the retreat, confirming the slowing, confirming what the physics said would be happening and what the fossils would later confirm had always been happening, all the way back to the beginning. And the beginning, and what the rocks have kept of it, and the corals, and the ancient mud of tidal flats that no longer exist, is where the night takes us now. There is a paleontologist named John W. Wells, and in 1963 he was holding a piece of coral in his hands. Not living coral, ancient coral, dead for nearly 400 million years, preserved in the kind of dense, mineralized quiet that only very old stone possesses. He was holding something from the Middle Devonian period, a stretch of time so remote that the word remote does not quite reach it. 400 million years ago, give or take, when the continents wore shapes no map has ever shown, when the seas lay over land that is now mountains, when the first forests were only beginning to spread their shallow roots across the edges of the world, and when the creatures that would one day leave footprints and build fires and turn a piece of their ancestors' skeleton slowly in the light of a laboratory did not yet exist in any form that would have been recognizable as ours. He was looking at the surface of this coral, and he was counting. Corals grow in layers. This is something the living ocean still demonstrates, something you can observe in a modern reef if you cut a thin enough section and lay it under a sufficiently patient eye. Each day, a coral secretes a thin band of calcium carbonate, a layer so fine it is closer to a film than a wall, and over the course of a year these daily increments accumulate into a slightly thicker seasonal band, the whole structure readable, if you know what you are reading, the way tree rings are readable, or the layered pages of sediment at the bottom of a lake that never quite forgets what year it was. The daily bands are the innermost units of this record. They are faint lines, each one representing a single day in the life of an animal that had no concept of days and no interest in keeping records, yet kept them anyway, faithfully, in the carbonate of its own skeleton. Wells counted the daily bands within a single year's worth of coral growth, and the number he found was not 365. It was closer to 400. 400 daily growth ridges in the space of what the coral's seasonal rhythm marked as 1 year. Which means that when this coral was alive, when it was drawing minerals from a Devonian sea, extending its tiny incremental skeleton toward the light that filtered down through water that had never been touched by a human hand, the year contained roughly 400 days. Not because the year itself was longer. The year, the time it takes the Earth to complete one orbit around the Sun, changes only negligibly over geological time. But if the year held 400 days rather than 365, then each of those days must have been shorter. The arithmetic is simple. Divide the year's fixed length by 400 instead of 365, and each day comes out closer to 21.5, perhaps 22 hours long. The day in the Devonian was somewhere between 21.8 and 22 hours, a day that was still recognizably a day, still a complete rotation of the Earth, but a rotation that was faster, a world that was hurrying in a way ours no longer does. 400 dawns in a single year. This is what the coral recorded, without intention, without awareness, merely by the regular biochemical rhythm of its own existence. An animal fastening itself to the seafloor of a world that spun more quickly than ours, laying down its daily thread of stone. And in doing so, leaving a message that waited in the rock for 400 million years for someone to read it. Wells published his findings, and they were extraordinary in their implications. Because here was not a calculation made from equations, not a number derived from theoretical models of planetary physics, but a physical measurement, a count, a thing you could point to in the material of the past and say, there is one day, and there is the next, and there are 400 of them, and when you are finished counting, you will know something true about the speed of the ancient world that no other method could have told you so directly. The fossil clocks were real. The rock remembered, and it was not only the Devonian corals that remembered. Later studies extended the pattern further back in time, into the Carboniferous, into the Ordovician, following the growth ridges of corals and other shelled organisms through progressively older formations, and in each case the count confirmed the same relationship. The further back in geological time, the more days in a year. The shorter each day, the faster the Earth was spinning. The numbers were not always easy to extract, and the interpretation of daily versus monthly versus annual bands in ancient skeletal material requires care and expertise, and the occasional acknowledgement that the counting is imperfect. But the trend was consistent. The evidence pointed in one direction. The Earth had been slowing, steadily, measurably, across the whole deep reach of time. It is worth pausing here for a moment, in the middle of what Wells found and what it means, to simply allow the strangeness of it to settle. Every coral alive during the Devonian period experienced 40 more sunrises per year than we do. Every dawn of that ancient world came around roughly 2 hours sooner than the dawn of our world comes around, the sky brightening at a slightly higher frequency, the sun crossing the sky in a slightly shorter arc, not visibly shorter to any creature standing there watching. Because no creature standing there watching would have had any memory of a longer day to compare it to, but shorter by the measure of physics, shorter by the record of the stone, shorter by 2 hours that tidal friction had not yet had time to steal. The clocks were running faster, the world was younger, and it moved accordingly. But the corals were not the only clocks the ancient ocean kept. There was another kind of stone record, laid down in a different kind of place, by a different kind of process, and it recorded not just the length of the day, but something finer and stranger, the rhythm of the tides themselves, pressed into the thin repeated pages of ancient mud. Tidal Rhythmites. The name is precise and somewhat technical, but what it describes is something you can understand if you have ever watched a tidal estuary for a full cycle, watched the water rise and fall twice in a day, watched the sediment it carries settle when the current slows, watched the layered accumulation of material that tides leave behind in the shallow places where water meets land and neither quite wins. Each tidal cycle deposits a layer of sand or silt whose thickness depends on the strength of that particular tide. A layer so thin you might not notice it, so regular in its repetition that it builds, over years and decades and centuries, into something that a geologist can open like a book. The daily layers record the tides of individual days. The fortnightly pattern of alternating thicker and thinner layers records the neap and spring cycle, the twice-monthly rhythm driven by the moon's changing angle relative to the sun. The longer patterns record months, seasons, and years. In other words, tidal rhythmites are stone tide gauges. They are the record of a tide that no longer falls on that shore, preserved in rock. Readable in its structure by the same logic that makes a barcode readable: regularity of pattern, variation of thickness, the grammar of repetition that encodes information about the world that created it. The most famous of these records is a formation in South Australia called the Elatina Formation. It is roughly 620 million years old, 150 million years older than the Devonian corals Wells was counting, and correspondingly deeper into the Earth's faster past. The Australian geologist George Williams spent years analysing the Elatina rhythmites, measuring their layers, interpreting their patterns, and the numbers he extracted from them told a story consistent with everything the corals had suggested, but extending it further back into a more remote period of the Earth's history. Quick reminder: after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. The Elatina record implies roughly 400 days per year at that ancient time. A day of approximately 1.9 hours, and because the number of months per year can also be inferred from the fortnightly pattern, something close to 13 months in a year rather than our 12. 620 million years ago, the Moon was completing its orbit around the Earth slightly more quickly than it does now, and slightly more frequently in each year. Because the year itself had not changed, but the Moon was closer and therefore moved faster, and the Earth's day was slightly shorter. The Elatina rhythmites did not simply confirm what the corals suggested. They extended the confirmation backward by another 220 million years, into a world so old it predates the first complex animal life. Into a time when the oceans of Earth held no shells to collect, no skeletons to fossilize, no growth rings to count. And yet the mud at their edges was still writing down the record, still keeping time in its slow way, still building the stone archive that would eventually be lifted by tectonics, exposed by erosion, found by a person with the patience to read it. And further back still, deeper into the Proterozoic, into the age before the Elatina Formation was deposited, lies another rhythmite sequence in the mountains of Utah, the Big Cottonwood Formation. Roughly 900 million years old, nearly a billion years, a number that should perhaps be allowed to sit quietly for a moment before it is passed over. Because a billion years is the kind of duration that has no human equivalent, no analogy in individual experience, no reference point in the span of any civilization, any language, any story ever told. 900 million years ago, the interpretation of the Big Cottonwood Rhythmites suggests that the day was somewhere in the range of 18 to 19 hours long. Shorter still. The Earth was spinning faster still, the Moon was closer still, and its tides were stronger and more frequent, pressing their fortnightly signature into the mud of ancient estuaries that have since been buried, compressed, folded by mountains, and carried by plate tectonics to an elevation in Utah that looks nothing like a tidal flat, but still contains, in its layered stone, the memory of one. These three fixed points, the Big Cottonwood Rhythmites at 900 million years, the Elatina Formation at 620 million years, the Devonian corals at 380 to 400 million years, form a line of evidence that no single calculation from physics alone could provide. They are measurements. They are physical counts of real ancient intervals, locked into material that survives precisely because the Earth is old enough and its geological processes are patient enough to have preserved what the living world wrote down and then forgot. The fossil clocks are not metaphors. They are clocks. The stone is the face, the layers are the hands. And if you know how to read the language of sedimentation and growth, you can open any one of them and ask what time it was. The rocks remember. This is perhaps the strangest and most calming thing about them. They do not choose to remember. They do not curate or select. They simply accumulate the record of what the world was doing when they were being formed. And they preserve it without judgment, without decay, without the softening that human memory applies to everything it holds. A piece of the Elatina formation does not know that it is 620 million years old. It does not know that someone will one day carry it into a laboratory and measure its layers under a microscope and extract from it a number for the length of an ancient day. It is simply there, as it has always been there, as it was when the Precambrian Ocean was still washing over the flat of South Australia, and it will continue to be there, unchanged in its information, long after the hands that measured it are themselves part of the geological record. But the fossils and the Rhythmites, extraordinary as they are, do not reach into recent history. To measure the slowing of the Earth's rotation over the last few thousand years, the period closest to us, the period in which human civilizations flourished and built and watched and wrote, a different kind of clock is needed and a different kind of record. And this record also exists, though it was left not by ancient animals and not by tidal mud, but by the shadow of the moon moving across the face of the Earth at the moment of a total solar eclipse. Solar eclipses were watched and recorded by some of the earliest astronomical cultures. Babylon kept systematic records of astronomical events for centuries, tablets of cuneiform inscription noting the dates, and observed positions of celestial phenomena with a precision that sometimes surprises those who encounter it expecting crudeness. China maintained astronomical records with comparable diligence across an even longer span of time. Greece and the medieval Arab world added their own observations. The result, accumulated across more than 2,500 years, is a body of eclipse data that tells astronomers not merely that an eclipse happened on a certain date, but precisely where on the surface of the Earth it was observed, and therefore with a small but significant step of reasoning, where the shadow of the moon was falling at that moment, and therefore what the geometry of the Earth-Moon-Sun alignment was at that instant. The reasoning that this enables is elegant. If the Earth's rotation had been perfectly constant across those 2,500 years, then the calculations of where an eclipse should have been visible, calculated backward from known orbital mechanics, would exactly match the historical records of where it actually was observed. But they do not match. There is a systematic drift between the predicted and the recorded positions of ancient eclipse shadows, a drift that grows larger the further back into history you look, and whose direction indicates that the Earth was rotating slightly faster in the past than the orbital calculations alone would suggest. The Earth, in other words, has been losing time relative to the sky. The two astronomers who turned this discrepancy into a rigorous measurement of rotational slowing were F. Richard Stevenson and L. V. Morrison, who compiled and analyzed eclipse records spanning roughly 2,700 years, working through the cuneiform tablets and the Chinese chronicles and the Greek records and the Arab observations, correcting for the ambiguities of ancient timekeeping and extracting from this unwieldy archive a number for how much the day has lengthened. Their analyses showed the Earth's rotation slowing at a rate close to, but slightly less than, what you would expect from tidal friction alone. The difference is real and has a real cause: the ongoing rebound of the Earth's crust from the weight of the great ice sheets of the last ice age, ice that melted roughly 10,000 years ago, releasing its pressure from the land beneath, allowing the crust to slowly, viscously rise again in a process called post-glacial rebound. As the crustal mass redistributes upward from the polar regions, it subtly shifts the distribution of the Earth's mass toward the equator, and just as a spinning figure skater slows by extending her arms, the Earth, pulling mass slightly outward, spins very slightly faster as a result. It is a small effect, measured in the eclipse records as a modest correction to the tidal rate. But it is real, and it is measurable, and its inclusion resolves the discrepancy between the pure tidal prediction and the historical observations. What the eclipse records ultimately show, accumulated and calculated into a single number, is that over roughly 2,000 years the difference between where the clock says the sun should be and where the sky actually shows it, a quantity called delta T, has grown to something on the order of several hours. Several hours of drift accumulated 2 milliseconds at a time over 2,000 years, the quiet sum of every lost fraction of a second adding up to a gap that is now large enough that if you were standing in Babylon 4,000 years ago, synchronized to the same clock we use today, you would find the sun rising hours later than you expected, because the Earth has turned a few hours further in total than the steady atomic rate would have predicted. This number, that several-hour drift in delta T, is what 2,500 years of eclipse records bequeath to the study of the Earth's rotation. Not a model, not an extrapolation, a measurement drawn from the written records of human beings who watched the sky above Babylon and Nineveh and Chang'an and Baghdad, who noted what they saw and wrote it down on clay and silk and parchment, and who could not have known that what they were preserving was not merely astronomical curiosity, but a calibration data point for a measurement that would not be made until centuries after. Their own civilizations had passed into history. They were, without intending it, building an instrument. And Stevenson and Morrison, working through that instrument's accumulated readings, were able to confirm what the corals had suggested and the Rhythmites had deepened, and the lunar lasers had placed on an absolute footing. The day is getting longer, has always been getting longer, and the rate at which it is doing so is something we can now measure across spans of time that range from months to billions of years. The mathematics beneath all of this, the theoretical framework that predicted tidal friction and its consequences before any of the fossil clocks or eclipse measurements had confirmed it, was worked out in the 1870s and 1880s by a man named George Darwin. The name is not accidental. He was the fifth child of Charles Darwin, the astronomer and mathematician, where his father had been the naturalist, and he approached the problem of the Earth, moon system, with the same patient, systematic thoroughness that his father had brought to the study of species. George Darwin asked what tidal friction would imply, mathematically, for the history of the moon's orbit, and he worked through the equations with the tools available to him. Pen and paper and the considerable analytical machinery of 19th century mathematical physics, and what he found was that the moon must once have been very much closer to the Earth, that the day must once have been very much shorter, and that the two bodies were connected by an ongoing exchange of angular momentum that was, in its slow way, transforming one into the other. George Darwin's tidal friction mathematics endure. The specific hypothesis he built upon those mathematics, that the moon was once flung from a molten, rapidly spinning Earth as a fluid droplet of rock, the so-called fission hypothesis, did not survive later scrutiny and has been replaced by the giant impact model, the collision with Theia, the debris disk that gathered into the moon we know. But the mathematical structure he laid down for how tidal friction works, how it transfers angular momentum, how it drives the recession of the moon and the lengthening of the day, this is still the foundation on which modern calculations are built. He derived it from first principles by reasoning about the forces involved and the conservation laws that govern them. Without the benefit of laser ranging or atomic clocks or any of the precise instruments that would later confirm his conclusions. He got it right. There is something quietly remarkable about this. A man in the 1870s, sitting with his equations, working out on paper the ancient history of the moon's orbit and the young Earth's spinning, arriving at conclusions that would not be directly confirmed until 90 years later, when the Apollo astronauts left prisms on the lunar surface and scientists began bouncing lasers off them and watching the moon retreat year by year at the rate his mathematics had anticipated. The physics was right. The patience of the confirmation simply had to wait for the instruments to catch up. This is not unusual in science, but it is always worth pausing over, this idea that careful reasoning about the structure of a system can reach forward into a future that has not yet built the tools to check it, and be found correct when those tools finally arrive. Darwin published his work. It was read by those who could follow the mathematics, which at the time was not a large community. And it settled into the literature as one of those papers that the field absorbed without fully digesting, present but not yet activated by the data it predicted. The data would come, eventually, from places Darwin could not have anticipated, from coral growth ridges counted by a paleontologist a century after his death, from tidal mud in South Australia and Utah, from the cuneiform records of Babylonian astronomers, from reflectors left on the moon by astronauts, from atomic clocks ticking in laboratories. All of it confirmed, each in its own language and at its own timescale, what he had worked out by the logic of force and conservation, and the patient geometry of orbiting bodies. The story of how we know what we know about the lengthening day is therefore not one story, but several, layered over each other, each using a different clock and a different archive to reach the same conclusion from a different direction. The fossil clocks reach back 400 million years and further. The eclipse clocks reach back 2,500 years. The laser ranging reaches back to 1969. The atomic clocks reach back to 1972, when the first leap seconds began. And the mathematics reach back to the 1870s, when George Darwin put down on paper a description of a process that the Earth had been performing in complete indifference to being described for 4.5 billion years. They agree. All of these methods, all of these scales, all of these archives, the ridged skeleton of an animal that lived in a Devonian sea, the layered mud of a Proterozoic tidal flat, the cuneiform notation of a Babylonian astronomer watching a shadow cross a city. They agree that the day is getting longer, has been getting longer, will continue to get longer, and that the mechanism driving this is the same in each case, operating at the same speed on the same principle, the moon pulling the tidal bulge, the bulge pulling the moon, the angular momentum moving slowly and permanently from the spinning of the Earth to the circling of its satellite. This agreement across methods, across scales, across kinds of evidence, is not something to move past quickly. It is the thing that makes the conclusion solid. Any single line of evidence can be questioned. The counting of growth ridges has its ambiguities. The interpretation of eclipse records depends on assumptions about ancient timekeeping. The laser measurements are precise but recent. But when every available kind of clock, reading every available kind of archive, from stone laid down 1 billion years ago to photons bounced off aluminum mirrors 50 years ago, all point in the same direction, the conclusion they point toward is not merely a hypothesis or a model. It is something the Earth has been doing, and something we have learned to read in all the materials the Earth has left behind. The ridges in the coral, the layers in the mud, the shadow on the ancient city. The laser returning to its detector from a distance of 384,400 kilometers, arriving back a fraction of a second later this year than it did last year, the difference amounting to approximately 3.8 centimeters of additional distance. The moon moving away at the speed of a growing fingernail, the day lengthening by less than 2 milliseconds per 100 years, the deep accumulation of all these small changes adding up over the span of time that the Earth and Moon have had to work with, to the difference between a 6-hour day and a 24-hour one. And there is more, because the story does not proceed smoothly from the fast young Earth to the slow present day in a simple, uninterrupted line of deceleration. There is something stranger in the middle, a long pause, a stillness buried in the Proterozoic, a period during which the day apparently stopped lengthening, during which the breaking and something else, something atmospheric, held each other in a balance so precise that the clock barely moved for what may have been 1 billion years. And to understand that pause, it is necessary to think about what else the sun does to the Earth besides illuminate it. Because the sun is not merely a source of light, and its effect on the planet's rotation is not merely the same as the moon's, and the relationship between them, at a certain day length, becomes something altogether unexpected. The day was growing longer, as it had been growing longer since the moon formed, and at some point in the middle of the Proterozoic, as the evidence from the Big Cottonwood Formation in Utah suggests, it had reached somewhere in the vicinity of 18 or 19 hours. And there, if the reading of the rocks is correct, it appears to have stayed. There is a question that follows naturally from all of this, a question that anyone who has been following the mathematics closely might already be turning over, and it is worth pausing on, because the answer to it opens something unexpected, something that changes the shape of the whole story. The question is this: if the moon is retreating from the Earth at 3.8 centimeters per year, and if that rate has held, then you can run the numbers in reverse, the way you might rewind a clock, and calculate where the moon was at any earlier time. 100 million years ago, it was about 3.8 meters closer. 1 billion years ago, about 38 kilometers closer. And 4.5 billion years ago, at the moment of formation, the moon would have been only a few hundred kilometers from the Earth's surface, which is to say essentially inside it, which is physically impossible, which is not where the moon began. And yet the giant impact hypothesis, supported by the chemistry of lunar rocks and by the physics of planetary formation, places the moon's birth at a distance very far from zero, tens of thousands of kilometers away, not a handful. So something does not add up. If you simply extrapolate the modern recession rate straight back through time, you do not arrive at a young moon just formed from the debris of a great collision. You arrive instead at a moon that appears to be only about 1.5 billion years old, a moon that does not exist, a moon that the rocks on its surface and the physics of its origin flatly contradict. This is called the lunar recession timescale problem, and for a while it looked like a serious difficulty for the entire theory, a fault in the mathematics, a place where the careful reasoning threatened to come apart. But the resolution is not a correction to the theory. The resolution is a correction to the assumption buried inside the extrapolation, the assumption that the modern rate is the ancient rate, that 3.8 centimeters per year is what it has always been, that the pace of the moon's retreat has held as steadily as the theory does. That assumption is wrong. Not dramatically wrong, not in a way that overturns anything fundamental, but wrong in the way that any simple extrapolation is wrong when the conditions it extrapolates from have not always held. The moon's recession rate is not a fixed constant of nature. It is a consequence of how effectively the Earth's oceans transfer tidal energy, which is to say, it is a consequence of the geography of the seas, the arrangement of continents and ocean basins, the depth of the water and the shape of the coastlines, and the way the tidal bulge sloshes back and forth across the planet's surface. And those things have not been constant. The continents have been moving for as long as the Earth has had continents, and the oceans have opened and closed and rearranged themselves countless times across the span of billions of years, and with each rearrangement the efficiency of the tidal transfer has shifted. Sometimes the geometry of the seas has placed the tides near a natural resonance, amplifying their energy transfer enormously, pushing the recession rate high. At other times, the geometry has been less favourable, the tides less efficient, the moon receding more slowly, the breaking gentler. The modern rate of 3.8 centimeters per year is, by geological standards, anomalously fast. The current arrangement of the Atlantic Ocean, still relatively young in geological terms, happens to place the tidal system near a resonance that makes it unusually effective at draining angular momentum from the Earth's spin. It is a coincidence of present geography, not a fixed truth about the Earth-Moon system. For long stretches of the Proterozoic and earlier eras, when the continents were arranged differently and the oceans moved through different basins, the rate was likely much lower, the moon retreating more slowly, the day lengthening more gently. And when you model those changes, when you build reconstructions that account for the wandering of the continents and the opening and closing of ancient seas, the numbers reconcile. The moon is where it should be. The theory holds. This is one of the things that make deep-time science so quietly beautiful. The apparent contradiction does not break the story. It deepens it. It forces you to see that the present moment is not a template for all moments, that the rate at which the world changes has itself been changing, and that the Earth we live on now, with its particular arrangement of oceans and land, is a specific configuration among many that have come and gone, each one altering in subtle ways the pace of the slow planetary clock. We happen to live in a time when the clock is running a little fast, and here is where the story grows stranger and stiller and more interesting, because among all the possible paces at which the day might have been lengthening, there appears to have been one particular length of day at which the lengthening nearly stopped altogether, at which the breaking of the moon's tidal pull found itself matched almost exactly by something pushing in the other direction. And that length of day was somewhere in the vicinity of 19 hours. The proposal comes from a study published in 2023 in the journal Nature Geoscience by researchers Mitchell and Kirscher, who examined evidence across a range of geological records and proposed that for roughly 1 billion years during the Proterozoic, the length of the Earth's day appears to have plateaued, holding near approximately 19 to 19.5 hours instead of continuing its steady climb toward 24. 1 billion years is a long time to be nearly still. It is longer than the entire span of complex animal life on this planet. It is a pause so extended that calling it a pause almost understates it, because from the perspective of any creature living within it, it would have seemed like permanence. The day was simply what it was. It did not change. And the reason it did not change involves the sun doing something that it does quietly, every day, that most people do not think about when they think about what the sun does to the Earth. The sun heats the atmosphere. This is obvious, and yet the consequences of it for the rotation of the planet are not obvious at all. When sunlight warms the air, it does not warm it uniformly. There is a region of maximum heating, a band of warm air that tracks roughly with local afternoon, a bulge of slightly denser and differently pressured atmosphere that moves around the planet each day with the turning of the sun. And that bulge, like the oceanic tidal bulge raised by the moon, has mass, and mass exerts a gravitational effect. And the gravitational effect of this atmospheric bulge is a torque, a force on the planet's rotation. But here is the key difference. While the moon's tidal bulge acts to slow the Earth's spin, this atmospheric thermal tide, as it is called, acts to speed it up. The two tides pull in opposite directions. They are in competition. Under ordinary conditions, the moon wins easily. The oceanic tidal bulge is far more massive than the atmospheric one, and the moon's braking torque is far stronger than the atmospheric thermal tide's accelerating push. The day lengthens. The moon moves outward. The competition is real, but one-sided. Except that the strength of the atmospheric tide depends on how closely the period of solar heating aligns with the natural resonant period of the atmosphere itself. Every system has a resonant frequency, a rate at which it responds most strongly when driven. A child on a swing responds to pushes timed to the swing's own period. A wine glass sings at a specific pitch. And the Earth's atmosphere, when driven by the daily rhythm of solar heating, responds most strongly when the length of the day is near a particular value. The hypothesis proposed by Mitchell and Kirscher is that around 19 hours, the length of the day came close enough to this atmospheric resonant period that the thermal tide was amplified, strengthened, made far more powerful than it would be at other day lengths. And at that amplified strength, the atmospheric push came nearly into balance with the lunar pull. The two torques cancelled. The day stopped growing, and this balance, once achieved, would have been self-sustaining for as long as the resonance held, for as long as the atmospheric dynamics and the solar heating cycle and the geometry of the Earth's orbit kept the conditions roughly stable. The estimate is that they held within this narrow window for perhaps 1 billion years. This remains, it should be said, a hypothesis. A compelling one, supported by evidence, published in a respected journal, taken seriously by researchers in the field, but not yet a settled conclusion. The exact duration of the plateau, the precise day length at which the balance occurred, the mechanism by which the resonance eventually broke, and the day resumed its lengthening. These are all questions that the geological record has not yet answered with the kind of clarity that would close the debate. The rocks carry the memory, somewhere, of that long, quiet billion. Reading it precisely enough to nail down the details is still a work in progress. What can be said with reasonable confidence is that something happened in the Proterozoic, that the evidence from places like the Big Cottonwood Formation in Utah points to a day of around 18 or 19 hours at a time when a simple extrapolation would have expected it to be longer, and that the proposed mechanism of an atmospheric tide in resonance with the sun is a physically coherent explanation for why the breaking paused. And then the pause ended. The day resumed growing. The continents kept moving, the oceans rearranged themselves, the resonance broke or drifted or was overwhelmed, and the moon's breaking reasserted its long dominance, and the clock began ticking forward again, adding its tiny fractions of a second per century, stretching the day slowly outward toward the 24 hours of the present. The billion-year stillness became the past, folded into the rock, legible in principle if not yet in every detail, waiting for the next researcher who reads the layers carefully enough to tell us more. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And the clock, having resumed, has been ticking ever since, right up to the present moment, right up to tonight, right up to this particular night on which you are listening and the earth is turning beneath you at a rate that is itself not quite what it was. There is a small, strange wrinkle here, a footnote to the long story of the slowing day that is easy to miss because it runs in what feels like the wrong direction. The tidal breaking is real, and over geological time it is the dominant trend, the iron certainty underlying everything. But riding on top of that long trend, visible only in the precision of modern atomic clocks, are shorter wobbles. Fluctuations in the Earth's rotation rate, driven by things happening inside the planet and on its surface, motions in the molten iron of the outer core, shifts in the distribution of mass caused by melting glaciers and the movement of water between oceans and ice sheets and aquifers, the redistribution of atmosphere from one season to the next. These wobbles can make the Earth spin slightly faster or slightly slower over periods of years or decades. And recently, in the years between 2020 and 2024, the Earth has been spinning a little faster than usual. Several of the shortest days ever measured by atomic clocks have occurred in this period, the planet completing its rotation in fractionally less than 24 hours, not by much, not by anything you could feel, but by enough to register precisely on the instruments that track these things. The reasons are not entirely settled, but the observation is clear. For a brief window, the trend went backward, not by much. Not in a way that contradicts anything about tidal friction or the long arc of the slowing day, but enough to raise an interesting question that scientists have been quietly discussing. If the Earth keeps spinning slightly faster than expected, at some point the atomic clocks might run ahead of the sun's actual position in the sky, and correcting for that gap might require removing a second from civil time rather than adding one. A negative leap second, something that has never been done. The long breaking still wins. Over any geological timescale, the day is getting longer, unambiguously, inexorably. But the short-term wobbles are a reminder that the Earth is not a simple machine, that the rotation is affected by everything happening on and in the planet, and that the precision with which we now measure time is fine enough to catch fluctuations that no previous era could even have detected. All of which brings the story around to where it is eventually going. If the breaking continues, if nothing interrupts it, if the physics plays out to its logical end, then there is a final state toward which all of this has been tending since the moon formed 4.5 billion years ago. And that final state is a kind of locking, a synchrony, a mutual stillness. The moon is already locked to the Earth tidally, in the way that means it always keeps the same face toward us, its rotation period equal to its orbital period, showing us forever its near side and keeping its far side forever turned away. That locking happened to the moon long ago, when the Earth's tidal pull on the young moon slowed its spin down until the two periods matched, at which point the breaking stopped. Because there was no longer a leading tidal bulge, no longer any torque, just a moon holding one face toward us with a kind of permanent, unhurried attentiveness. What is happening to the Earth now is the same process, just far slower, far less complete, because the moon is much smaller than the Earth and its tidal pull is much weaker than the Earth's was on the moon. But it is the same physics. The Earth's spin is being slowed toward the point where the length of the day matches the length of the moon's orbit, where Earth too is tidally locked, showing the moon forever the same face of its own, the two bodies holding each other in a mutual stillness like two dancers who have finally stopped turning. At that point, the day and the month would be the same length, somewhere in the vicinity of 47 of our present days. A year would contain not 365 days, but roughly 8 of them. The sun would creep across the sky with an almost geological slowness, taking weeks to travel from one horizon to the other. The face of the Earth pointed toward the moon would never see it rise or set. The face pointed away would never see it at all. This is not a speculation. This is the direction the physics points, and it points there clearly and without ambiguity. It is only the timescale that is staggering. The full tidal lock would take tens of billions of years to complete, a span of time so large that it makes the current age of the universe seem like a brief preamble. And this is where the story encounters its own interruption, the thing that will intervene before the lock completes. The thing that means the Earth's rotation will never actually finish the journey it has been on. In approximately 5 billion years, the Sun will have exhausted the hydrogen at its core and will begin burning the hydrogen in a shell around the core, swelling outward into what is called a red giant. It will expand, slowly at first and then more dramatically, until it is many times its current size, engulfing Mercury and Venus, and possibly reaching as far as the orbit of the Earth. What happens to the Earth and Moon at that point is uncertain in its details, but it is certain that the inner solar system will be transformed in ways that dwarf any tidal rearrangement. The slow dance of the Earth and Moon, the patient transfer of angular momentum across 4.5 billion years of careful braking, will be overtaken by an event so much larger that the tidal lock will never have the opportunity to complete. The day's lengthening is real. The moon's retreat is real. The eventual lock is the direction of travel. But the journey will be interrupted, as so many long journeys are, by something that was always going to happen on a different timescale, and the final destination will not be reached. The day will be longer then than it is now, and longer still after that, stretching slowly outward through whatever billions of years remain. And then the sun will change everything, and the particular story of the Earth's slowing rotation will end not with a resolved lock, but with something far more total, the end of the conditions that made the story possible at all. There is one more small thing worth mentioning, a quiet consequence of the moon's retreat that plays out over the same vast timescales, and that is, in its way, one of the more affecting details in all of this. The moon is moving away from the Earth. Every year it is 3.8 centimeters farther. That distance matters for something we take rather for granted. Those rare moments when the moon passes directly between the Earth and the Sun and covers it completely. When the bright disk disappears behind the dark circle of the moon and the corona blazes into view and the sky goes a dark purple-grey in the middle of the day, and birds stop singing and the temperature drops, and for a few minutes the world is different. A total solar eclipse is possible only because of a coincidence of apparent sizes. The moon is roughly 400 times smaller than the Sun in diameter, and it is also roughly 400 times closer, and those two facts precisely cancel, making the moon and the Sun appear almost exactly the same size in our sky. A slightly smaller moon or a slightly larger one, and the match would be imperfect. And the moon is moving away. Every year the match is very slightly worse, the moon's apparent disk very slightly smaller relative to the Sun's. Over millions of years this matters. Eventually the moon will be too small in the sky to fully cover the Sun. Total solar eclipses will become impossible. What will happen instead is that the moon will pass across the face of the Sun and cover only its center, leaving a ring of sunlight around the dark disk, what astronomers call an annular eclipse. The ring of fire rather than the vanishing. That is the future of eclipses. Eventually, the total ones are ending, and they have been ending since the moon was first formed. And every one that happens now is one that will not be possible much longer, on the scale of deep time. And all of this, the slowing day and the retreating moon and the ending eclipses and the distant tidal lock and the sun growing old while the dance continues, all of it is happening right now, tonight, beneath you and around you, silently and without interruption. The tides are moving in the water, and they are moving in the rock, and the energy they carry is bleeding slowly away from the spin of the planet and into the moon's outward drift, and the moon is somewhere above the horizon tonight, or below it, pulling on the water with the same patient gravity it has always exerted, and the earth is turning in response. And the day is lengthening by a fraction so small it has no name in ordinary speech. This is the thing that is hard to hold in the mind, but that becomes, once you let it settle, enormously restful. The day is not a fixed thing. It was never a fixed thing. It is the current state of an immense, slow process, a process that began before there was any life on this planet, that continued through the first bacteria and the first complex cells and the first animals and the forests of the Carboniferous and the dinosaurs of the Mesozoic and every human civilization that has ever built anything, and that continues, still, tonight, while you lie here, while you breathe, while the darkness outside holds whatever the darkness outside holds. The 6-hour day of the young earth, so bright and short and loud with tides, is gone. The 19-hour plateau of the Proterozoic, that billion-year stillness when the atmosphere and the moon held each other in balance, is gone too. The 22-hour day in which the Devonian corals put down their 400 growth rings per year is gone. The 23-and-a-half-hour day of the last dinosaurs is gone. And what remains is this, a 24-hour day, approximately, still lengthening, still giving a fraction of itself each century to the moon's outward drift, still carrying in its very length the accumulated memory of everything that slowed it. George Darwin, sitting in the 1870s and 1880s, with his pen and his mathematics, working out the angular momentum of the Earth-Moon system and realizing for the first time that the Moon must once have been enormously close, that the tides must have been hundreds of times stronger, that the day must have been far shorter, did not know about tidal rhythmites or about the Big Cottonwood Formation or about the Elatina shales of South Australia. He had not counted fossil coral growth rings, and he had not bounced a laser off a retroreflector left on the lunar surface by the crew of Apollo. He had only the equations, and they told him something astonishing, and he followed them. And they were right. The rocks confirmed it decades later, and the lasers confirmed it again, and each confirmation added another layer of solidity to the same slow story. John Wells, in 1963, counting the daily ridges in a piece of 400-million-year-old coral with enough patience and enough precision to conclude that the year in which that coral lived contained 400 days, was not making a guess. He was reading. The stone had kept the account, and he was reading it. Every year that passed during the Devonian, the coral laid down a growth band for each day, and then a broader band for the season, and the ratio of the one to the other was the number of days in the year, and the number of days in the year was the length of the day, and the length of the day was the state of the Earth-Moon system at that moment in deep time. It is written. It has always been written. The Earth keeps its own records in forms patient enough to survive hundreds of millions of years. The Babylonian astronomers who recorded eclipses did not know they were making measurements that would eventually be used to track the slowing of the Earth's rotation. They were recording extraordinary events, things that darkened the sky in ways that demanded attention, that carried meaning in their systems of thought, that needed to be noted and kept. And the records they kept, passed down and translated and eventually read by researchers like Stevenson and Morrison, turned out to be a clock. A record of where the moon's shadow fell on a particular day in a particular year, compared with where the laws of orbital mechanics say it should have fallen if the Earth had been spinning at its present rate, gives you the accumulated drift. The measure of all the slowing since that day. The cumulative difference over 2.5 millennia of eclipse records amounts to several hours. The world has turned a little more slowly with each generation than the generation before. And you are part of that sequence. Not in any dramatic or conscious way. But the day you were born in was a few milliseconds longer than the day your grandparents were born in, and the day you might imagine a grandchild being born in will be a few milliseconds longer still, and none of these differences are perceptible, none of them alter the quality of a day in any way you could feel. But they are real, and they are the continuation of a process that has been real since the moon formed, and they connect this night to all the other nights that have preceded it across 4.5 billion years of the Earth's turning. The night is long, or feels long, in the way that nights feel long when the mind is quiet and the body is still. And the day that follows it will be, by the most precise measurement available, exactly as long as today, and the day after will be the same, and for any ordinary reckoning of a human life, the day will not change at all. But somewhere beneath the ordinary reckoning, beneath the reach of anything we can feel, the tidal friction is doing what it has always done. And the moon is a fraction of a millimeter farther from the Earth tonight than it was this morning, and the day is, over these 100 years, becoming a fraction of a second longer, and the slow exhalation continues. There is something in this that belongs to the same feeling as lying in the dark and listening to the house settle. The small sounds of a structure adjusting to the temperature of the night, each sound barely audible, each one a tiny release. The Earth is doing something like that, on a timescale too large to perceive, settling into a slightly different configuration with each passing century, the spin easing, the moon drifting outward. The day lengthening so slowly that 100 human generations would not notice a second's difference. And there is comfort in this, if you let it in. Not because the process is gentle in any human sense, but because it is so vastly larger than anything that requires your attention tonight, so entirely beyond the reach of anything you carry with you into the dark. Whatever happened today, the Earth's rotation is not among your responsibilities. The moon will continue its slow retreat without your assistance. The tidal bulge will continue to move through the ocean basins and across the shallow seas, draining the Earth's spin by its few terawatts, heating the water by the faintest measurable fraction, nudging the moon outward by 3.8 centimeters per year, year after year, whether anyone thinks about it or not, whether anyone is awake or not, whether the night is restless or still. If you are somewhere in the world right now where it is dark, or nearly dark, or where the quiet has come, it would be good to know where that is. The people who listen to these slow stories come from everywhere, and there is something worth knowing about the fact that the same night, the same turning of the same planet, is holding all of them at once, each one horizontal somewhere, each one letting the day go. You have done what today asked. You have carried what today weighed. The planet will continue turning without your help, and the moon will be exactly where it should be, a few centimeters farther than it was when you were born, which is to say exactly where 4.5 billion years of patient physics have placed it. The tides will move in the dark. The coral in the deep water will add, eventually, one more band to its record. The stone will keep its account. Let the deep thoughts settle, and let yourself sink with them.